Hello everyone. Can you hear me okay?
Yes.
Fantastic. So let me go ahead and share my screen. Okay, I'm assuming you see a slide deck.
Yes.
Fantastic. So yes, thank you for the introduction. My name is Riley Hickman. I'm a PhD student at the University of Toronto, supervised by Alana Spiro-Guzik. It's really great to be here at the inaugural MMLI Symposium. It's a real honor for me to be here amongst yes, this really esteemed group of professors, industry partners, postdocs, and excellent graduate students. So I'd like to thank you in advance for your attention, and also all the amazing staff that the MMLI has for setting up the symposium. So today I'd like to talk to you about Bayesian optimization of matter. So this is we'll cover, I guess, my graduate work so far in using tools from model-based optimization to actually optimize matter, whether it is drug formulations, whether it is photovoltaic materials, process parameters for chemical reactions. That's what I'll talk to you about today. So I'd like to start off with this quote from Peter Thiel, who's a Silicon Valley investor. He said at the Gardner Symposium in 2014, we've seen innovation in bits, but not enough in atoms. So if you just let that sink in, I guess in the last 20 years or so, we've seen a lot of development in the digital era. So much so that when you ask the layman about technological innovation, their mind probably immediately goes to mobile applications, artificial intelligence, web apps, etc. But Peter is of the belief that the digital era has kind of underwhelmed a little bit, and we need to get back to making tangible things, making matter, making atoms. And here we are a few years later, and it looks like others are starting to share that opinion. So here I've kind of posted two articles, one from the Harvard Business Review and one from Barron's, which both generally have the same thesis, that the digital era and the hype around the digital era is coming to an end. And with the end of this era, new innovations with different technologies will be ushered in, such as material science, which is an area in which both of these articles highlight as being an extremely valuable field of study in the coming decade. So I guess my research and the thesis of this talk will be, how can we use tools from the digital era to accelerate innovation in this new era of technological innovation? And I could argue that there's many of such tools, but today I'll be focusing on machine learning. So there's been a plethora of, I guess, machine learning algorithms that have been proposed to be beneficial for the materials discovery pipeline. And sometimes it's easy to get lost in all of these tools, and it's difficult to kind of identify where they fit in. So here's a very simple schematic that I drew up. On the x-axis here, or the horizontal axis, we have the progress toward a new material through the ideation phase, the research and development phases. And on the vertical axis, I've kind of shown the expense of a property measurement. How expensive is it to measure the figure of merit for a new material? Now, typically there is a correlation between how close you are to a new material and how expensive it is to measure that material's figure of merit. So typically tools in machine learning like generative models are more useful, where you can evaluate the property or the figure of merit very quickly. But as you get into the research and development phases, these measurements become much more expensive. So you want to ask your algorithms to be more sample efficient. And this is where something like Bayesian optimization, or more generally model-based optimization, continues to kind of be the gold standard for sample efficient global optimization. So my talk will talk about Bayesian optimization, and specifically how to use this tool to optimize materials, to do inverse design on materials. So Bayes-Opt, like I said, is typically regarded as the gold standard in sample efficient optimization. And it's so efficient because at each iteration, we train a machine learning model known as a surrogate model on all our available observations. Then from that model, we're able to compute an acquisition function, which can be queried for new experiments to perform. And Bayesian optimization is extremely flexible because you can use essentially any machine learning model you want for the surrogate model, and you can use different acquisition functions for different applications. Now, in the Aspera-Guzik group, we looked at Bayesian optimization, which has been this tool that's been around for 30 or 40 years. And we said, what is lacking in this tool that experimental scientists need? And the answer is quite a bit. So we've developed this kind of experiment planning Bayesian optimization ecosystem where each of the circles you see on the screen here is an algorithm. And each of these algorithms can work together in tandem to enable Bayesian optimization for the experimental sciences. So kind of going around the horn here, starting from Phoenix and Griffin, which are kind of core novel Bayesian optimization strategies, going around to adding constraints on the parameter space, which is very, very prevalent in experimental sciences, enabling multi-objective optimization, multi-fidelity optimization, robust optimization to noise on input parameters, and also enabling community accessible benchmarking of different experiment planning strategies for realistic applications. So unfortunately, I don't have time to talk about all of these algorithms today. I will just focus on a few, starting with some of our novel contributions to core Bayesian optimization techniques. So a very popular surrogate model to use in Bayes-Opt is the Gaussian process. But a few years ago, our group reimagined Bayesian optimization as kernel density estimation based. So we developed this algorithm called Phoenix, which I guess infers kernel densities using a Bayesian neural network and constructs a surrogate model, this alpha of x, using a weighted average of those kernel densities. And from that surrogate model, we can construct an acquisition function by weighting this average by a sampling parameter lambda. And this gives us our exploration trade-off, which is typical of Bayes-Opt, which is what gives it this powerful global optimization ability. Now, Phoenix only works for continuous valued parameters. So in experimental sciences, this could be something like time, reaction time, temperature, pressure, etc. But typically, especially chemists are often tasked with simultaneously optimizing categorical valued parameters, such as molecules, variables that don't have any inherent order, as well as tuning continuous process parameters. So this could be optimizing a reaction where you choose the solvent, you choose a catalyst, and you simultaneously optimize for reaction time and temperature, for instance. So we extended the ideas in Phoenix to this algorithm called Griffin, which can handle categorical valued parameters. Now, Griffin is very similar to Phoenix, and I won't go too much into the math here, but essentially, instead of using Gaussian kernel densities, Griffin supports kernel densities on the simplex. So we use this Gumbel softmax or concrete distribution. And what Griffin allows one to do is use descriptors of the categorical variable options. So these could be physical, chemical descriptors of molecules, for instance, to accelerate the search. Now, Griffin, we've used Griffin in numerous applications so far, including kind of the optimization of photophysical properties of organic laser molecules. In this study, we published in ACS Central Science, where we looked at photophysical properties of good lasing molecules, as well as synthetic accessibility. A very important aspect in practical Bayesian optimization, though, is extending to parameter spaces which have constraints. So we've kind of distilled the complicated taxonomy of constrained optimization down to two types. So known and unknown constraints. Known constraints are known a priori by the researcher. So this could be something like, if you're mixing two liquids, their combined volume can't exceed that of the reaction vessel. Is a simple known constraint. Unknown constraints have to be determined on the fly. So these could be the result of failed experiments, abandoned syntheses, unstable molecules or materials, etc. So basically, iterations where you don't have a property measurement, you're returned a nan or not a number value instead. So the no constraints approach is very conceptually simple. So we basically just constrain the acquisition function of our algorithms to avoid the infeasible regions. So we're technically solving this constrained optimization problem where the constraint function C of x has to map to a feasible value. And we've implemented a really flexible kind of Python interface for this type of optimization. We've applied it, I won't go into too much detail here, but we have applied it to kind of process constrained optimization of Buckminster-Fullerian adducts that are useful for photovoltaic applications, where the, I guess, protocol is subject to process constraints on the flow rates of the reagents. So this seems to work pretty well. We see really good performance of our Griffin algorithm compared to computing algorithms. For unknown constraints, it's a little bit more interesting because we actually need to kind of resolve the constraint function on the fly. So for this, we actually implemented a Bayesian classifier, which on the fly learns the decision boundary between feasible and infeasible points. And with the hope is that we can combine that with the acquisition function of our Bayesian optimizer, such that we can avoid infeasible measurements, sort of predict them as we go. So this is kind of a depiction of our classifier in action. The top row here shows, I guess, infeasible measurements as red crosses and feasible measurements as blue crosses. And the heat map represents the output of our classifier. So it's a probability that indicates the algorithm's belief that this parameter point is feasible. And in the bottom row, we've kind of shaded on the true constraint function. And we see that we're able to kind of approximate this with a modest number of observations. And we're currently benchmarking ways to kind of combine the feasibility prediction with the actual acquisition function of the algorithm, and to see which provides better optimization performance, and which tends to avoid infeasible measurements most. So this is work underway in our group. One other thing I wanted to tell you about very quickly is Bayesian optimization with robustness to uncertainty on input parameters. So typically in I guess vanilla Bayesian optimization, we make the assumption that the parameters that the algorithm recommends are actually the same ones exactly that enter the experiment. Now, of course, in practice, this is very difficult to do, as you can have noisy liquid dispensing, you can have noisy solid dispensing. Humans aren't perfect in how they, I guess, dispense parameters to the experiment. So typically you have noisy inputs, just like this dopant robot you see on the right here. There's quite a bit of scatter. So we came up with this algorithm called Golem. And the idea with Golem is to optimize not for the objective function, but for a robust version of the objective function, which is average best case under some distribution of noise on the input parameters. So I won't go into too many details, but we come up with this really efficient approach using random forests, actually, which let us discretize a really expensive to evaluate integral. And we're able to do this robust optimization with any Bayesian optimization algorithm. And we published this in Chemical Science this year. Very, very quickly before I end, I want to highlight some, I guess, applications of these algorithms at the University of Toronto. So we published a bunch of studies with prototypes of these self-driving labs, which essentially means that the coupling of our experiment planning algorithms with high performance computing and or automated laboratory equipment. So the first of which is this collaboration with the great Eugenia Kumacheva, where we're optimizing for targeted nanoparticle synthesis with targeted spectroscopic qualities. So we're optimizing this kind of seven-dimensional process parameter space for these UV-Vis spectra characteristics of the nanoparticles. The next is another collaboration with the Kumacheva group, in which we're optimizing combination cancer therapies for breast cancer. So we're looking at this kind of elaborate microfluidic platform where we, I guess, expose these BCSs to some combination of drugs, I guess, assess their efficiency with fluorescence imaging using computer vision, and feed it back into the optimizer, which recommends the next set of drug concentrations, dosage profiles, so the administration time and dose duration. So that's going really well, and it's really exciting. The last thing is optimization of process parameters for high accuracy liquid dispensing. So in doing really sensitive chemistries, sometimes we need like a microliter accuracy for liquid dispensing. And one size does not fit all in terms of recommended process parameters for different solvents. So here we're optimizing over this big process parameter space to I guess maximize accuracy and precision. Yeah, so I just want to conclude saying that this is not perfect. There's still like a really far way to go in automation in the laboratory. It's not a solved problem, which I think is one of the great things that this symposium will kind of target. How do we do this? And yeah, with that, I'd like to conclude. I'd like to thank everyone at the MMLI, at UIUC, at the Vector Institute, at the University of Toronto, my supervisor, some of my senior mentors in the group, as well as the rest of my group. So like I said, it's great to be here, and I hope you enjoyed the presentation, and I'd be happy to take any questions.
Thank you, Riley. Sir, we probably have time for one quick question. So if you're in person, you have a question, there are microphones up the front. Please come up and ask your question. Or if you're online, please raise your hand. You have a question, Marty?
Oh, I'm sorry. I'm having a bit of trouble hearing.
I think we're turning it on.
Can you hear me now?
Yes, loud and clear.
So you've looked a lot into how to optimize the AI algorithms to solve problems. I'm wondering, what do you think are like currently key limitations in AI that are like ready for somebody to come in and innovate? Where are we missing new AI tools to help solve problems?
Great question. I think so. I think typically the Bayesian optimization literature in itself is pretty rich with various niche applications. But I think in chemistry, dealing with chemistry or material science, I think dealing with noise is a very unique issue. So innovating on robust kind of machine learning for noisy measurements or noisy input parameters. Also potentially using some more state-of-the-art tools like meta learning. So learning from prior optimization campaigns to kind of transfer knowledge over to a novel related optimization campaign might be low-hanging fruit. But I think a lot of the space to innovate comes in, I guess, reproducibility of these things, or self-driving platforms in general, transparency, reporting, I guess, standardized like procedures to do this, data sharing, so having like robust databases and user interfaces to access previous optimization runs. There's a lot to do. There's a lot to do. Also, data analysis is always something that can be innovated on. So advanced like plotting, how to infer insights from this data to be delivered to humans. So it's very very young. There can be lots of innovations, I think. Yeah.
Great. Thank you, Riley.
Thank you.
So I'm now really excited to introduce our keynote speaker today, Dr. David Baker, who's joining us virtually from the University of Washington.